Let's continue our look at the conservation of momentum with a different example. Recall the conservation of momentum just simply means momentum of a system of objects is never going to change. So let's have a big old cube here of clay. Alright, and let's say it has a mass of 60 kilograms. Alright, and let's have a bowling ball over here, and let's say it's got a mass of about 7 kilograms, and say this bowling ball is cruising along here at about 1.58 meters per second. Alright, so the velocity of the bowling ball, 1.58 meters per second. Alright, and so the clay here has a mass of 60 kilograms, as we said, but let's have it not moving. Let's say its speed is 0. So it's just sitting there. Alright, and so our system is just going to be these two objects, the bowling ball and this big block of clay. That's our system. And this time let's look at it in terms of what we call an inelastic collision. Inelastic collision. Alright, and so hopefully you can see that if we have the bowling ball going here to this big block of clay, that it's going to stick in the clay. So in inelastic collision, the objects typically stick together. So in here, so we'll have the collision, so the bowling ball runs into the block of clay, and so after the collision, the block of clay is now has a bowling ball stuck in it. Alright, so we've got one object now, and still our system, right? Still our closed system here. We have just the bowling ball and the clay, and so we want to look at how fast is this combination moving at this point. Right? How fast is this bowling ball and block of clay moving at this point? So again, it's tough to use the idea of the conservation of momentum. The total momentum that we have here, right, has to be equal to the total momentum that we'll have after the collision. So whatever the momentum is the two of the objects before, it's going to be the same after. And we'll be able to use that to solve this problem here. So let's look at the blob of clay real quick. Since it's not moving, right, the momentum of the clay is just going to be 0. Right, it's mass times velocity. Don't forget, momentum is just mass times velocity, and we have no velocity, so we have no momentum. The bowling ball over here, however, does have some momentum to start with. It's moving. So our bowling ball, right, our mass of our bowling ball times the velocity of the bowling ball will give us our momentum. So we'll just plug those numbers in right there. We have 7 kilogram bowling ball, and it's moving at 1.58 meters per second. And that should give us a momentum of the bowling ball of about 11.06 kilogram meter per second. Okay, so there's the momentum of the bowling ball, again, as it's moving in towards the block of clay. So our total momentum is the momentum of the bowling ball plus the momentum of the block of clay. So we have no momentum from the block of clay, so our total momentum is just the momentum of the bowling ball, in this case 11.06 kilogram meters per second. And that is still going to be the momentum after they collide and stick together. So it's still 11.06 kilogram meters per second. Now, the difference in this situation than our previous elastic collision was that now these objects have stuck together. So we want to figure out how fast it's going. The momentum of this one object must be the total momentum of the system. So I'm going to take a look at that. So the total momentum now is equal to the mass of the combination times the velocity altogether. So my momentum was 11.06 kilogram meter per second. And the mass, now we have both of these objects stuck here together. So the mass is actually the mass of the bowling ball plus the mass of the block of clay. So I've got a 7 kilogram bowling ball stuck in this 60 kilogram block of clay. So my total mass is actually 67 kilograms now. So I have a mass of 67 kilograms. And all that times the velocity of those. So I'll divide out the 67 kilograms on both sides. 67 kilograms. And that goes away. And so I get a velocity of about 0.17 meters per second. So the whole situation is kind of looking at the conservation again. So we've got this bowling ball moving along in the direction to the left here. So that total momentum was also going to the left, right? And then after the collision, it's still going to the left. So our velocity is still going to the left. So all our positive signs indicate that we're going to the left here. The combination of these two, the velocity is actually less than it was than just the bowling ball itself. So in order for the momentum to be conserved, since there was more mass in this one single object, the velocity had to be less so that you still end up with the exact same momentum. Remember, momentum has both mass and velocity components to it. So if we change one, like we changed the mass here, then the velocity has to change accordingly. So again, the momentum was conserved, and this was just an example of an inelastic collision where the objects stick together.